the organizer for giving me this opportunity. Also, this work will be some long history. Started 5 years ago, try to do molecular dynamics with the quantum Monte Carlo, and something is going on only very recently. So I will show. I will try to show also very recent results that begin to make sense somehow. So this work is the main work has been done by a PhD student, Guglielmo Mazzola, that comes from Trento, from Pederiva. So it's also nice to thank. So this is the plan of the talk. So molecular dynamics with quantum Monte Carlo is a dream, and it's my dream personally. And I have, because we can do somehow prediction of structure, phase transition, and all we are interested in solid-state physics. And for doing this, I have done, I will try to describe essentially 3 or 4 paths. One is to find a good variational wave function that can be describe qualitative feature of the correlation and also quantitative in an accurate way. Then how to compute forces with the quantum Monte Carlo and the efficient calculation of forces, and introduce the damped molecular dynamics that also a key ingredient to have reasonable simulation with reasonable computational time. And then I will try to do some examples that I hope are interesting for you. So the wave function, I've just cut a long story, but if you have a question, please interrupt me. And essentially started from lattice model. And Anderson, long time ago, proposed that in order to describe a spin liquid, so very peculiar state of matter that cannot be understood by band theory, so somehow it's a representation of an insulator when a band is half-filled, so only the spin degrees of freedom are relevant. The very nice proposal was that in order to represent some insulator in which only the spin degrees of freedom are relevant, we start from a BCS wave function, which is, you know, you couple particles with opposite spin and opposite momentum, and then the important ingredient, this wave function will be superconducting, so nothing to do with an insulator, the opposite. Then you project in the right subspace in which there is only one spin for each side. I'm talking about a lattice model like Hubbard model or Heisenberg model. Then you get a representation of an insulator, which is quite important because with this paradigm one can explain also ITC superconductivity, why we have superconductivity at low doping, etc., etc. But for this case, what I want to emphasize that this paradigm wave function is very easy because somehow we don't have the problem. For instance, suppose that in a triangular lattice, the wave function, the correct wave function is built by several singlets. You have to connect all possible nearest neighbor singlet in the original formulation of Anderson. With this wave function, it is enough to create a pairing function with only nearest neighbor singlet. So this is a superconducting wave function, but in real space, the f is just short range. And then you project, and automatically you have a wave function that is done of all these possible elements, and is a very good wave function for the description of the triangular lattice. Of course, now we know that most likely triangular lattice is an order that, so quite trivial system, but the wave function is still very accurate. So how to do in how to translate this know-how that has been done in lattice mode to continuous system? Well, we need two basic ingredients. One is mean field description, that is, as we have learned from Anderson, can be a generic BCS wave function, projected on the given number of particles. So, and the projection is done, as usual in Monte Carlo, in configuration space. So you take a configuration in which the electrons are in a given position, and you have that the so-called anti-symmetrized geminal part. When you project on a given number of particles, this is called AGP. Is a name borrowed by quantum chemists. And you have to compute a determinant, so something that is computable, in which the rows and the columns just are represented by the coordinate of the electrons with spin up and spin down. And then we have a generic Jastrow factor that takes into account the electronic correlation. On a lattice, we want to project, for instance, project out configuration in which two electrons are on the same site. In the continuous case, we have to do a nu that is very strongly negative, so that suppress the amplitude of this wave function when the electrons are too close. And in principle, we have to be able to optimize both functions of two coordinates. So how to parameterize a function of two coordinates? When I borrowed this by the standard quantum chemistry approach, you can define an atomic basis with Gaussian or exponential or whatever. You can also do a linear combination centered on a given atom. I represents some center, and I, capital R I, is an atomic center. And then you can build on this basis, you define a matrix that acts on this atomic basis. Of course, if the basis is complete, you can reproduce any function. Of course, by increasing the basis, you have an automatic control of the convergence of your wave function to the lowest energy if you want to optimize the energy. Of course, you see immediately what is the main problem, that even if the basis is small, for instance, you have 100 hydrogen and you have only one orbital for hydrogen, you have 100 by 100 essentially parameters to optimize. So it's 10,000. So this is one of the main problems that we have to solve. So the Jastrow factor is the same. It's the same function of two coordinates. And in order to be as unbiased as possible, one has to use the same approach. So we use, of course, a slightly different basis, but in principle we can converge in the same way. So let me emphasize what is the difference with compared to density functional theory. So in density functional theory, the approach is very simple. You have the density, and God give you the functional, and you have to minimize the density given the functional, and you know that if the functional is very good, you have get very good result. But this is always a problem. Now this is more straightforward, but of course it's much more complicated. You have two functions, one for the correlation, it is one, and one for the mean field part, if you want, BCS. And you have to minimize of the energy, so the expectation value of the energy upon these two functions. So it's difficult, but not impossible, compared to the full many-body wave function. The full many-body wave function is a factor of n variables, so it's very difficult to represent. So let me emphasize the basic difference in the approach that we have been using is given by the Jastrow factor. So this function of two variables. In order to be efficient in the representation, to have the smallest possible basis to represent this Jastrow factor, one has to satisfy the known so-called cusp condition. There are important exact results for the many-body wave function. So we have that when two electrons goes to arbitrary close, this function has to go like this. So it's a singular because it's the distance, so the square root of the sum of the coordinates. And also when we are close to an atom, this has to be satisfied. So the most simple thing is to introduce this simple function that essentially removes all the singularity of this general function, and all the rest is some smooth function that can be parameterized with a very small basis, hopefully. But this is the complicated part. Again, we have to use an atomic basis with the similar form of the determinant and to optimize the matrix, so a huge number of parameters. This kind of parameterization was introduced almost 10 years ago in our group. So why we have to be so complicated with the Jastrow? Well, the main reason is because we know that there are long-range interactions. The most famous one is the van der Waals interaction. I don't know if you are aware of that. So if you have two atoms, two atoms at a very large distance, we know that the interaction between the two atoms is given by this form, where this is the coordinate of the electron reference to the atom A. So if you want, it's a difference. So a variational wave function should allow the second order contribution in the energy, because the second order gives you the van der Waals, which, as you know, goes like 1/r⁶. And only if it is compatible with this first order in U. So what is very simple to check that, so if we want to parameterize the Jastrow factor U, it has to contain this term, e to the minus. Roughly speaking, it's not a very rigorous argument. But you see that these are, if we want to represent this term, we have to have around the atom A and around the atom B orbitals that are not simple rotational invariant, but have to have p-wave character. So this is the reason that we have, and these terms are contained in the general factor. So it's important that you have a Jastrow that depends both on the relative distance between the atom A, the atom B, and the two electrons. So it's so-called four-body terms. The four-body terms has never been implemented, as far as I know, in most of the Jastrow part. So I want to show how is important this term in one striking example. In the beryllium dimer, this is a very difficult molecule. Well, okay, which has a very short bond length and nevertheless has a very weak binding. So it's very strange, and many methods fails. So if you do R3 fork, for instance, you are not able even to bind the molecules. They like to repel, which is against, because you should have the van der Waals interaction that is attractive. A big success of DFT was that you bind the molecule with DFT, but this binding is completely nonsense. But nevertheless, this was a big success, because quantum chemistry were in the early, were wandering around, try to correct the R3 fork in a simple way, and the local density was a very big success. I will show that still this is the big problem in DFT, no? Our competitor. I will show some recent result. I don't know, maybe there are other attempts, but essentially, these van der Waals corrections are put by hand and in some are system dependent, sometimes work. If you want to do something that makes sense in the sense of that you derive, the simplest thing is to do the RPA, and you get some crazy energy as a function of the position. The only reasonable calculation have been done by using CI with several determinants, and these are actually our work that I will emphasize later on. So essentially, quantum chemistry have solved the problem, just use several determinants. So billions. CI and I don't know, couple cluster to 4 or whatever.
DFT is still fighting with this.
Still fighting. It's still fighting. They don't have any clue on this beryllium. Instead, in our approach, at least if we find a mean field solution, no, that works together with the Jastrow, we can understand what is the clue. And at least if you have a billion of determinants, I see, okay, you reproduce the experiment, but you don't understand what is going on, at least if you don't do. So the real problem in this molecule is that you have the hybridization between the 2s and 2p orbitals is a key ingredient, and this can be understood without correlation because also Hartree-Fock can hybridize. No? But together with this, there is the correlated van der Waals interaction, and dealing with two altogether in a consistent approach, so far, you cannot do. Instead, we have a variational wave function that has both this ingredient and this. Just we take Hartree-Fock as a Slater determinant and the Jastrow with the 4-body term, and we get, well, exceptionally good for a single determinant, which is not perfect. It's not perfect. This was published 3 years ago. All the results are the black points. Then, just for curiosity, I wanted to see how stable is the result if I improve more the convergence in the basis set. And I increased the basis set a little bit. I included also 2d orbitals. You remember the P generates the van der Waals, the D probably the next leading order, 1 over to the 8 or whatever. And you see that, I mean, you get a remarkable improvement, especially in the long distance part. So this is
so what are the squares in there?
The square is the calculation that we have done with Maria Piamarchi in 2010. Instead, the red wine are the most recent result that I have not even published. I have published in a book some calculation, but a recent few months ago I obtained, just with a larger basis. And sorry, I want to emphasize another point, that the optimization, simultaneous optimization of the Jastrow and the determinant is important because in this case you can change slightly the nodes, no? And you can have completely wrong results, of course. I don't know, I have not done the DMC over this, but I will tell you. I have not shown, but I will tell you what is the DMC story in a few seconds. You get that the longer distance part, that is the most correlated part, is completely off. So if you take the DFT as a determinant and you optimize only the Jastrow. In our approach, we optimize always all together. And
Can I ask, why is your DMC result below the experiment here? Because I think the numbers are pretty...
no, these are VMC, not DMC, and this is the reference to the 2 atomic.
Oh.
So you can be below. Actually, DMC is much below, overbinds. You know the problem, no?
Yeah.
The reference is the 2 atomic energy.
But I mean, the atom you calculate
With the same method.
with the same method.
Optimizing in the same basis, etc.
How far is your atomic from the exact atomic?
It's not very good. Is R3-4. I've done only R3-4, not IGP. You mentioned this. Let me remember. Is 92% of the correlation, something like that. Yeah, but this is a well-known problem here. I mean, okay, and this is done also by quantum chemistry when they do CI or whatever. They have, the assumption is that the atomic degrees of freedom are high energy part, and so you don't need to approximate very good. So they start with R3-4 and they froze the core electrons, or they don't allow too much, and they define an active space only in the valence part. If they do this, also in their approach, the atom is not very good, because you have not the core low energy. And actually, I think I am not a good energy, but the atomic energy is also better of the CI, what they do in CI. I think this may be a discussion, because quantum chemistry is able to reproduce Berylllium-2 with this recipe, and I have been able to reproduce with this recipe. Tell me.
I mean, in atom, the error on R3-4 nodes versus exact nodes is about 10 milliarcties, and here the energy difference which you are talking about.
That's the same hypothesis. Also in quantum chemistry, you have very big error on the atomic. In fact, I want to say the remarks, and I have remarks. So certainly if you don't use the 4-body, you are not able to bind. You can look to the literature. Cyrus Umrigar with the 3-body does not bind. So this is important. If you do the DMC, you overbind, so you go a little, it's 40% below, which is quite sizable in this scale. It's a very small energy, because the binding is very small. So this is interesting to understand why it happens. Maybe the experiments are wrong. I've shown the experiments here. I don't know if you have appreciated, probably, no? This green line is the experiment. They do the experiment. They measure the harmonic frequency, and they build in an indirect way the energy as a function of the. So maybe DMC in this delicate case, since DMC is well known, does not conserve the spin, may have some spin contamination or angular momentum contamination, and can lose a little bit of accuracy, or the experiment may be wrong, and by luck, I am accurate. Also, this is interesting to mention that if you do a much better description of the atom, so you use the so-called antisymmetry, so you optimize full, you don't restrict this atomic solution to be a single slated determinant, but you do what you can with these BCS ansatz, you get a worse result, in the sense that you have only a tiny binding that is far from experimental. So this shows, in my opinion, that also in our work, when we use DMC, we have to exploit the possible cancellation between atomic and atomic wave function that fills the high energy degrees of freedom, and molecular binding that is very small. So now let us consider the second part of the wave function, which is the determinantal part. So as I have said, if you take a configuration, you write the determinant in this form. What is the relation with standard R3-4 orbitals? Essentially, you have a function of two variables written as a matrix. You simply diagonalize the matrix, and this may be considered molecular orbital, because phi k will be a linear combination of these atomic orbitals. And as you know, the molecular orbital has to be defined on all the atomic bases. What does it mean, this diagonalization? Well, essentially, suppose you have 48 electrons and you have only 24 non-zero eigenvalue different from 0. Then when you do the antisymmetrization, there is nothing to do. You have to fill these 24 states and you single out a simple slated determinant. Instead, if you have some weight in the unoccupied state, unoccupied within R3-4, you build up some correlation, so you gain energy certainly, and so within this wave function you can have the freedom also to describe also a superconductor, because if this tail remains in the thermodynamic limit, this is most likely a superconducting wave function. So I want to emphasize that this kind of wave function is a generalization of the slated determinant. It certainly should improve the energy, but maybe, as we have seen in the Berylllium 2, not necessarily improve the chemical bond. Well, as I emphasized, if you have this tail in the thermodynamic limit, you can have either a superconductor or the new thing that, as Anderson has pointed out, you can have an insulator, because the Jastrow kill the phase coherence, and you can describe also a qualitatively new phase of matter. So let me summarize. Essentially, when we do this variational approach, we can understand after the optimization what is going on in the physics. No? Lambda is essentially in the density matrix, C dagger C, as a function of distance, in a free uncorrelated system, and decays very slowly if you have a metallic. It decays exponentially if you have an insulator or a superconductor, and is in between if you have a gapless superconductor. Of course, correlation make dress this wave function in a more appealing way, because the Jastrow, as we have shown well, several years ago, if it is particularly singular, can turn a metal into an insulator, something that is possible also with DMC, so I was very curious to see that in this oxygen iron oxide, it was possible to do this with fixed node. And so the pairing state is not necessarily a superconductor, but maybe a Mott insulator. So we have some, within our variational wave function, we can describe something new. But in this kind of talk, I would like to emphasize that this representation is very useful for doing the optimization. Forget about, let us assume that we want to optimize the simple slated determinant in presence of the Jastrow. Well, the important thing that we have a dual representation. You can represent your slated determinant with molecular orbitals, as we have seen, and this part is 0. Or you can simply substitute in this molecular orbital the expression in terms of psi and get a particular lambda ij. The only thing that this matrix has to have only n alpha non-zero eigenvalues. The only restriction to be explicitly dual. So this is a very useful way to write a slated determinant, because what we can do, yes, this is the molecular orbital, as I have said, and is defined overall the space. So we can start with simple unbiased. So the Jastrow is 1, it means you don't put anything in the 3-body and 4-body. Of course, you put something in the cusp. You leave the cusp condition satisfied. You start with this equal to 0, and you take the molecular orbital from DFT. So you just plug in the DFT orbital here. and you have a very good initial way. Then you optimize lambda ij, because since this is perfectly legitimate way to represent, at most is redundant, but if you take this fix and optimize this, you can do. Of course, with the requirement that this matrix, all the matrix has only n half non-zero eigenvalue. It's a restriction on the rank. Then after you have lambda ij non-zero and the old one fixed, you can again rediagonalize the whole matrix, substitute the new, and re-optimize the lambda ij, and you can go until everything converges. Well, why is convenient, this approach? It's very simple, because suppose you want to satisfy translation invariance, so you have a solid. With molecular orbital is a mess. You have to use complex, and if you want to do the real representation, you get stuck. I mean, it's just, it's very complicated. It's possible, but it's very complicated. Here you have just to satisfy that the lambda ij is translational invariant, so you don't have many problems to satisfy symmetries. Then you can use locality. This is the most important thing that I have found recently, because you assume, suppose that you have lambda ij is the density matrix. This is easy to understand if you have an insulator, so it should decay. So if you restrict the calculation and you don't consider the variational parameters that are too far, so are connect localized orbitals that are too far, you can assume that there is no point to optimize the variational parameter, and you can exclude from the optimization. Immediately you realize that if you are allowed to use this locality, you go from n squared variational parameter to a much smaller. So you change the scaling, and you can do calculation even for large sites. So the above result, since in our calculation we restrict the wave function to be a Slater determinant, so to have only n half non-zero eigenvalue, this locality hypothesis works also for metals, because we put the ingredient that there should be a Fermi surface to begin with. So you can understand. Okay, this is an hypothesis that we have verified numerically. So we have considered hydrogen in metallic phase. You can optimize all with a lot of effort. I consider two systems, and you see the number of parameters as you increase this cutoff locality. So you don't consider here, you consider only the local part, only the orbitals connected by two atomic units, 3, 4, 5. You see the number of parameters increase dramatically, and if you want to do 256 electrons, you have to spend, you have to optimize a ridiculously large number of parameters. Instead, if you see how does converge the energy, if you start with DFT orbitals, you don't do a big error. No? So it's something like 0.01 eV per atom. So this is the error in the total energy. But you can see that you clearly converge very fast, even in the metallic phase, as a function of Rmax. And so we can stop even safely to distance 4 and optimize for 256 hydrogen only 5,000 parameters, which is reasonably fair. So this is one of the ingredients. So compact wave function that has the smallest number of parameters possible, but that guarantees the convergence, because I want to have convergent result. Then the other problem is, if we want to do molecular dynamics, is how to calculate forces. So we know that with the quantum Monte Carlo, we can compute energy as a function of the position of the atom. And suppose that you have many atoms, with not only the beryllium that contains 2 atoms. You have, if you do the straightforward approach, you have to compute 3m energy difference. And this became prohibitive very quickly. So you change the scale of the... Of course, there are several ways to solve this problem. What we have found very useful is to use the concept of algorithmic differentiation. Somehow there is some general theory by mathematicians that is heavily used by economists. Actually, my old PhD student is in a bank, so he knows this. That's why I met him, and he told me this stuff. And it says that essentially that you have any code, you can compute the wave function, and it takes some computer time. You can derive almost automatically another code that computes all the derivative of this wave function upon all the variational parameters that you have with essentially the same computer effort. Of course, if you squeeze your mind, you can understand that you can do also by yourself, but you have to play with several tricks, etc., etc. But the algorithmic differentiation gives you an automatic way to find the optimal algorithm, actually. If you have an optimal algorithm that gives you the psi given the variational parameter, you will have the optimal algorithm that gives you the derivative. That is amazing. And so this is very useful. And you can also use some automatic differentiation for the most stupid routine that are usually very long. The routine that tells you how is the Laplacian and the gradient of any of these localized orbitals, and you can do by clicking a button automatically. It's a code that can generate Fortran code. So it's very helpful. After you do this job, you can easily see that you can increase the number of atoms, and the CPU time for computing all the forces for all the molecules, for all the water in the molecules, essentially remains constant with respect to the variational calculation that computes only the energy. Essentially, you lose only a factor of 4 for more than 100 force component. For DMC, this factor of 4 becomes even smaller because DMC is even slower in order to create an uncorrelated sample. Of course, there is the problem of how to compute. Still, there is some discussion in literature. Maybe there will be some in this afternoon discussion how to compute DMC forces. And also, the point is that when you use pseudo-potential or a very complicated Jastrow like ours, if you want to do the derivative analytically, write the code, this becomes hopeless. So if you have this automatic black box, you know what to do, because routine by routine you have to define the parent routine that do the differentiation. This is very important, because otherwise the code becomes... Of course, after that you check that your calculation coincides with the finite difference calculation, and then you have done your job. So now we have efficient forces. So structural optimization in dynamics is possible with quantum Monte Carlo. That's the main hope. I want to acknowledge that the first attempt was done by Lubos and Grossman, to do the molecular dynamics by quantum Monte Carlo, but without Monte Carlo forces. So what we believe is that using forces we can have very efficient algorithm, and essentially we can find something, as I will show, that is sizably different from what are the DFT prediction. Because if you try to use DMC from your DFT output, you hardly find something very different from DFT, at least in the phase transition or whatever. So what we have to do is, what we have implemented is molecular dynamics with friction. Here R is the position of the atom, or the atoms. And the particular property of this approach is that gamma is a matrix, actually. It's a friction term, and can be taught as a matrix. This is the force that we can compute, and these are the velocity of the ions. I take unit mass for simplicity, and this is the random noise. As a matter of fact, if the random noise, the correlator of the random noise, satisfies the fluctuation dissipation theorem, then you are sure that the ensemble that you are computing with this molecular dynamics is just distributed according to the canonical ensemble, e to the minus beta Vt. This is important to use friction that is a matrix, because when you use Monte Carlo, you have noise in the forces. And the correlation between the noise component is not necessarily a trivial. There is a generic covariance matrix, as in the... And if we choose, but this noise is given for free, so if we choose at each step the friction matrix proportional to our covariance matrix that we can measure, because at each iteration we do a Monte Carlo step, we compute forces, and we can compute the covariance matrix of the forces. We essentially have for free the noise, and we can optimize the efficiency of the dynamics. This is the main point in few words. So, and the most important thing in the dynamics is to use a discretization, so you have to integrate this molecular dynamics equation for the largest possible time, so that you have the most possible uncorrelated measurement of your physical system.
Sandro, why? What is this must be trivial, but why you put yourself in the overdamped limit for this equation? I mean, in principle, the equation, the motion equation would still have inside some acceleration.
You are perfectly right. I have not said that I am in the overdamped region. I try to put the smallest possible friction compatible with the random noise that I have. Of course, there is a criteria. Well, suppose that gamma is the diagonal, essentially. Gamma 0 times c. Of course, this correlation exists, but is almost diagonal. According to there is an argument by Maury and Roberto Carr that say that this gamma 0 should be equal, is a dimension of a frequency, to the smallest frequency in the system. And actually we have verified that by end that if you choose an appropriate value, you have better performance.
You see it a posteriori, no?
A posteriori, yeah. You have, unfortunately, you don't know the frequency, but you know that if we increase the system, this frequency goes down, so you have to but if you cannot do too much down, otherwise you have to decrease too much the noise in your forces, and it becomes, so you have to find a compromise. Given in word, essentially, so let me emphasize this. In word, these equations are linear in V. So essentially, you can, once you give by grant this value, at least suppose that the ion position does not move too much, you are allowed to integrate exactly this equation for the velocity, no matter what is V. And this is what, because we want to be as accurate as possible, even when gamma is large. Gamma is not small at the end of the story due to this, at least in certain direction if you diagonalize the matrix. So you have to do this calculation. In word is a very simple, but then you have to do over algebra, you get crazy. So at the end, you find the solution on how to do. I want to show that it's a lengthy by straightforward calculation. And then you see that this is a sample on a water model in an external field. This is the energy difference with minus sign. And then you see that you can go to much larger delta compared to the standard Euler. This is very important for Monte Carlo because for standard molecular dynamics, they don't need to have the friction term. Here we need. So given that, we have preliminary calculation on 32 water molecules. This looks like a dream since a few years ago. Well, we don't know, we have not, this is 32 water, so still a little bit smaller. So we hope to do 64. And the other problem is that the error bar are quite huge. So of course, any any G of R calculated with DFT will be within this error bar. So at the moment, the results are meaningful, but are meaningless.
It's a matter of time.
It's a matter of time. So we have asked the grant for 30 million hours. This is few million, and we will have probably the grant approved, I hope. And we will try to do this calculation with 3 or 4 times smaller error bar.
Yeah, there are error bars, but it seems like the red curve is shifting.
Yeah, that's a problem. We have to find also whether this depends. There are 2 possibilities. According to DFT, this peak moves a little bit on the left when you go to larger size, so it may be a size effect.
Why is that?
It's only 32 water molecules.
It's only 32 water model.
But this is the percolation function.
The percolation.
Isn't that part only?
Yes, you are saying it's social, but there is, I mean, it's a matter of calculation in DFT, okay?
That might depend on the optimization of.
Also, it may depend on the optimization.
Optimize the functions of a small box. In principle, this is not what you get for a larger box. It tries to optimize all together.
Yeah.
And so you compromised a bit, and you may have. I see.
Nah, I know, it's work in progress. It may be that this is a bias to the basis that we have used.
There, I don't know, but I mean, when it comes to the hardcore, I would have thought that part you should,
But this is slightly dependent on size. You can see I cannot show here, but it's.
There's a conformational issue too, right?
Yeah.
These things are rotating, so in a sense, the hardcore is averaged over that
Maybe.
geometry.
We are curious. Maybe it's not because we neglect the quantum effect, so not necessarily we have to get the exact result. Our issue is whether with the quantum Monte Carlo, so with the correct description of the van der Waals ab-initio and no self-interaction correction, but at least we can say cleaner than DFT, we can get a comparison with the experiment. This is 300 Kelvin.
Yeah.
Okay, this is room.
Did you check your diffusion constant of a water molecule in there?
I think it's impossible. Yeah, I mean we don't have. It's even much more. You need much more. This is 2 picoseconds. So, in principle, to converge the structure, you should 40 picoseconds, and I think for the diffusion, you have to go to 100. Yeah. Also the density, no? The density and pressure, but I've tried to compute the pressure, the error bar. The pressure, we cannot say.
But eventually you can get it at some point,
Yeah. I think we need some tricks for the pressure.
But can you not use the GOR? Area theory. You would
The virial theorem.
correct, but more or less it's one.
Maybe. Yeah, that's a good idea. If we clean the error bar here, we should have a reasonable.
That typically has a smaller error bar.
Now, certainly, we have big error bar.
But it's always better to just take the difference of.
So let me talk more. So, well, I want to show that this was like a dream for me for up to, and now we begin to do calculation that, of course, we spend some million hours, but now some million hours.
We just say a lot of computer time.
Yeah, and the problem, this was done in Blue Gene with 2,000 nodes, so and no problem of parallelization. 2,000 nodes is 30,000 processors. So I mean, the advantage of Monte Carlo now, we can do realistic calculation using this huge computer. We can go to 300,000 probably with gene, queen gene. Okay. Yeah, I have problem of stupid cluster InfiniBand to scale, but I think it's a problem of InfiniBand or whatever. But on Blue Gene there is no problem. We have estimated that even 100,000 processor is not a problem even for this system. So this is. Now we go. I want to discuss, if I have time. I should have some time on hydrogen, the most recent and exciting result. So, so a metallic liquid is difficult to simulate without, because metallic is long range, it is lambda j. And usual simulation have been done for very small system. Instead, with this technique, with power of computer, we are able to do up to 256. Why our technique should be more efficient? Because if we use forces, each iteration we do, as we have seen, the calculation of VMC, but we have the possibility to move all the ion position with one-shot calculation. So it should be 256 more efficient than standard local update in Monte Carlo. And so let's start with the configuration which is atomic. You see that there are very few green. A green bond means that the two hydrogen are below a distance of 1.5. That roughly means that I do a molecular bond. Now I have to, I hope. So you start the simulation, and you see how much fast it moves. It looks really ergodic, I would say. Finally, I had a lot of problem with ergodicity before a few months ago, I would say. Now we have found the rule. Large delta, compact wave function, few parameters, and everything looks very nice. And you see that you form a completely qualitative different structure with several bonds. And this is a molecular liquid, if you want. So now there is the, well, first thing, the size effects are very important. So if you take this density, you have to go to very large system to get the right pressure. Of course, one can say we have only the gamma point. We should do k-average as is done. But usually k-average for a liquid does not make much sense. K-average for a solid clearly imposes the periodicity. And usual belief is that the gamma point is the best thing that you can do, and the only thing that you can do is to do larger and larger system. And so we have stopped here, and hopefully nothing changed here. The other thing is that the VMC maybe, many people say it is not very accurate. So we tried to do the DMC actually, well, LRDMC, but anyway, let's say that this is the difference between the pressure calculated. We take the configuration, there is a bias. We take the configuration equilibrated with VMC, and they compute the pressure with DMC. You see the difference is much less than the size effect. It's 10 gigapascal. The size effect is huge, 100 gigapascal. So it seems that is an acceptable approximation to use VMC with this complicated Jastrow. And this is what we get. So this you do several density, and at the beginning we were a little surprised. We get a completely smooth curve, and the people were finding the transition around here, but we never seen. So I asked Pierre Leone, where is the transition? Then we went to very high pressure and very tiny indication of the transition.
Yeah, the last 4 points.
600, yeah. So the main thing is that, as you know, what is the physics? When we go to low density, we go to higher pressure. You know that when we go to higher pressure, the system wants to metallize, want to become a metal. The kinetic energy is more important. And but we saw it's very difficult. It's very difficult to find a first-order transition, and to see, you should see a first-order transition by a plateau in the density versus pressure. So you should find, and instead you see only a minor difference here that suggests that there may be a plateau in between. But fortunately, we have a large enough system, and we can compute the G of R with a resolution of 0.1, 0.01. And here we see clearly that there is a first-order transition, because the G of R changes completely when we change by a tiny bit the density. You see that from here to here there is always a peak, and then suddenly almost disappear, but remain a little bit a peak. So the fingerprint of a first-order transition, there should be some change, immediate change in the code. If you do smaller system, you get everything is smooth, so you cannot identify the transition.
But it should be a first-order phase transition?
This is what Sandro Sorella. It should be a first order because metal insulator transition at finite temperature are always first order, as far as I know. There is an example, actually, strictly speaking, if there is no first order transition, you cannot distinguish a metal from an insulator, because there is always some activated conductivity even in the metal, in the insulating phase. Now you have a gap, but due to thermal activation you can have conductivity. Rigorously, you can think about metal insulator only at 0 temperature. But if there is a first order, we can say that there is, because you certainly see a jump in the conductivity. So the interesting thing that if you increase the temperature, this is more evident. This plateau becomes a little bit more evident. I don't say it's. But what I want to show is that, we have a phase transition between density 1.31 that should be a metal, so a larger pressure, and here it should be an insulator. So we take the atomic from an atomic G of R, so this kind of G of R. We take a configuration, and we start our molecular dynamics in the region where we have the molecular phase. You see that usually you have hysteresis if you have not an efficient Monte Carlo. No? You remain stuck in the same phase when you have a first-order transition. Instead, here with few hundred iterations, you essentially are able to converge to the same radial distribution and the same pressure. So this is very powerful, and that's why I begin to believe to our molecular dynamics. This is a crucial test that the things are working and are reproducible. I want to show the comparison with previous work. I would say, it's rather confusing. This has been done usually always by the same group, Seperli and co-authors. The first claim was that there was no first order, like us, we don't see because it was so huge pressure, the first order. But then they withdraw their claim, and a recent paper they say that by using DFT, not quantum Monte Carlo, but in somehow as better, they get a first order but in this range. They judge that this is a region where there should be the phase transition, so around 200 gigapascal. And instead we judge that is around about twice, so quite substantial difference. I want to say that why DFT? So DFT, this is an improved DFT. Why DFT should, in our opinion, underestimate the pressure, because the DFT, as well known, strongly underestimate the gap. So automatically favors the metallic, because they want to have a very small gap when you do your band structure, and so it's very easy to metallize DFT. Instead, when we do quantum Monte Carlo, we have not this bias. Maybe this we do some other error, but certainly we are not biased by this. And so we have the pressure at much larger value. So what is interesting that we discovered very recently is that the phase diagram of hydrogen is like this, and we are discussing about the transition between a molecular fluid and a metallic fluid. And the experiment suggests there was an experiment like here that claimed that there was a metallic hydrogen in this region. But they still see some molecular. What is proven? So instead we see that this, if there exists this transition at 600 Kelvin is at 500 gigapascal, and so it's pushed to very large. So why this contradiction? In our opinion, because experiments have to still wait that they are able to do much larger pressure. And we see that if we take this, we just monitored what is the average lifetime of pairs. So you have a molecular liquid, and you ask what is the lifetime of this, molecule. This should be related to the conductivity. One of the lifetime is essentially by the Born rule. Of course, is end-waving argument. And you see that before getting the real first order transition, you have, even much before you get that you can have strong signal of larger conductivity. So our opinion is that they still have to work to increase the pressure to find the real first order transition. So this is the conclusion. I have essentially realistic simulation of leaks are now possible, and we can do several ions with reliable, at least ergodic, I would say, that do not depend on the initialization simulation. The long-range interactions that are so difficult for DFT can be very easily described by our Jastrow factor. So we capture the most important ingredient that is very difficult to capture within DFT. And by using locality, we can do a reasonably small number of parameters even for large sites, so that we can do realistic simulation. And we hope to do better. I want to only thank all the collaborators in this project, all the postdoc and students that have contributed to the development of this code. Thank you very much.
More questions?
No question.
I may have misunderstood, but I wondered if, the noise that you're using for your dynamics, isn't that colored? Doesn't that matter? So it's not really a pure noise. It's colored by the.
Yeah, you want to know the details, so now we put the noise.
I was thinking the noise is coming from because it's a Monte Carlo.
Indeed, it was a little bit too sloppy in this description, because what we put is, this is just an example. In principle, we can use only the noise coming from Monte Carlo, but this is not convenient because you may have a lot of bias, no? So what we do, this gamma is essentially as a constant proportional to the identity plus, and the noise proportional to Monte Carlo, so being alpha, the covariance matrix, is if you look to the paper, maybe you can easily realize that it's proportional to the delta, the discretization. So in the continuous limit, so we want only to use the noise. Suppose that you have forces calculated with some error bar, and you want to do a calculation of finite temperature that is more or less correct. Of course, the noise of the force will influence your temperature. So if you take into account this, you may have not very accurate result. So we called this technique noise correction somehow, no? So we compute the covariance matrix of this in order to correct for the bias that we eventually obtain if we don't do any correction. This is the only, but of course we have to put real noise at the end. It's just in a standard Langevin dynamics.
It's more of a comment, but I mean, if one of these guys that did this HSE stuff, I'm not any kind of DFT fan, but HSE generally gets gaps correctly. So it's still interesting that it's so far off.
HSE?
That's the functional that
yes,
uses.
yeah.
Because it mixes in exact exchange, and that generally raises the gap up, and it's you know, it's certainly not tested in any regime like this, but if you use that functional on a variety of materials.
Yeah, they actually find that the transition change according to this functional. If you do the PBA, it's shifted by 100 gigapascal, but according to us should be shifted by 300. So it's
EXX is an orbital dependent functional. It's not a density dependent functional. It's more expensive actually to use that than to use conventional functionals. Much more expensive actually. And
HSC or what?
the EXX, the exact exchange functional.
Yeah, it's more expensive.
So there's hope that that can be used to solve these gap problems. But I think
no, they used that in that simulation.
Yeah.
Oh well, okay. So
that's why they use.
They use the HSC functional, which
yeah. But I'm saying in general, there's hope they can solve a lot of problems. This is the orbital dependent stuff, but it's not hasn't entirely succeeded yet. I think it's more expensive.
It improves it, but you never know how much, you know, so each time you are sort of shooting somewhere in there, which is reasonable, but it's never perfect, you know, you have no real justification why to mix exactly this amount.
Right, because it's, I mean, the problem of the gap is coming from two things, right? One is, and it does nothing for the fact that DFT doesn't mind having partial occupation or, you know, fractional particle numbers, which is a big part of it. And so in a way you could say it's probably overestimating.
Yeah, you're replacing one thing by another.
That's
or
right.
effectively,
But it's the usual thing of getting the right answer.
It replaces one thing by another, but effectively, since you have only one number and it correlates with the number, you sort of can get to the right number.
Okay. So there is no discussion this afternoon because there's nothing to discuss.
We're saving it up.
We can find some other.
We'll see.
Okay.
Okay. you very much.
Thank you again, Sandro.
Thank you to you.